The human forearm. I'm going to look at the human forearm in terms of moments. If we have the bones represented like this for simplicity, where this is the pivot point, the arm is holding a load of 50 newtons at this point, and we also need to consider the weight of the forearm itself, which we'll say is 25 newtons, acting at the centre. The other force is from the bicep, which will be acting upwards at around about this point. I'm going to simplify the situation now, just drawing this line to represent the forearm bone and the pivot point here. Adding the forces, we had the 50 newtons of the load at this point, the 25 newtons weight of the forearm at this point, and the force which I'll call F of the bicep at this point. We also need to know the distances these forces are from the pivot. So this we can say is 5 centimeters, the weight of the forearm acting 20 centimeters from the pivot, and the weight of the load acting 40 centimeters from the pivot. Now, the forearm is in equilibrium, so we can say that the sum of the clockwise moments will equal the sum of the anticlockwise moments. This force and this force are trying to move the forearm in a clockwise direction, and the bicep force is trying to move it in an anticlockwise direction. So we can write this down as 25 newtons times 0.2 meters is the moment due to the weight of the forearm, plus 50 newtons times 0.4 meters is the moment due to the load, must equal the anticlockwise moment, which is force F, multiplied by its distance of 0.05 meters. So we can rearrange for F to find that F is equal to the 5 Newton meter moment of the weight of the forearm plus the 20 Newton meter moment of the load divided by its distance from the pivot of 0.05 meters, meaning the force due to the bicep is 500 newtons. You see, because it is much closer to the pivot than either of the two other forces, it needs to be a very, very large force.